The Webb looks so far out that it's capturing light that's been travelling for over 13 billion years. But the universe has been expanding, and so the light has been stretching. And so for the most distant galaxies, we're looking back in time almost to the Big Bang.
The Big Bang stands as the definitive narrative of modern cosmology, a bold assertion that our universe had a beginning and possesses a finite age. However, the concept of a singular cosmic beginning, followed by billions of years of cosmic expansion, has faced skepticism since its inception, and doubters have challenged its validity. Within mainstream cosmology, doubts about the Big Bang largely dissipated in the 1960s with the discovery of the cosmic microwave background, which is a pervasive radiation buzz that aligns coherently as a remnant from the universe's early, hot era. Nevertheless, throughout time, doubts have persisted which have gained traction in recent times due to groundbreaking revelations from the James Webb Space Telescope in the early universe. In a stunning observation, NASA's time machine, the JWST, which has the capability of detecting 13 billion-year-old light as explained by famous British physicist Brian Cox, has identified an inconceivable mass of galaxies at the edge of the observable universe. This discovery has challenged the validity of the Big Bang theory. Now the question is, could it be time to entirely reshape our understanding of the cosmos and our existence? Let's dive in to find out.
Then the Hubble was not sensitive to that light, so that the Webb can see the formation of the first galaxies. It's essentially looking all the way back to very close to the beginning of time. And that's very important because we're not entirely sure exactly how those first galaxies formed. So we can see that. It's microwaves because it's been stretched so much by the expansion of the universe. Going back, the problem with light is that in those earliest times, the universe was so hot and so dense that light couldn't travel through it. So it was opaque. So you can't use light to go back earlier than that. But what we can potentially do, not yet, we're not good enough yet, but the technology we use now to detect colliding black holes, which is another remarkable thing, but I'll leave that one aside for now. But we have the technology to do that. And that technology possibly could allow us to probe right back to this thing, the Big Bang. And again, whether or not that's the origin of time, we can talk about as well.
The origin of the Big Bang concept traces back to the 1920s and 1930s. Observing distant galaxies revealed a peculiar pattern. The farther they were, the faster they seemed to recede. Following Albert Einstein's general relativity predictions, a static universe would be gravitationally unstable, necessitating either a divergence or a collapse if space adhered to its laws. The observation of the apparent recession taught us that the universe is presently expanding. As things move farther apart over time, it implies that they were closer together in the distant past. The expansion of the universe not only signifies increasing distances over time, but also entails the stretching of light wavelengths as we progress through time. Since wavelength corresponds to energy, with shorter being more energetic, the universe cools as it ages, indicating hotter conditions in the past. If we trace this expansion back far enough, we reach a point where everything is so hot that neutral atoms couldn't form. According to this scenario, we should detect a residual radiation glow today in all directions, having cooled to just a few degrees above absolute zero. The groundbreaking discovery of this cosmic microwave background in 1964 by Arno Penzias and Bob Wilson serve as a stunning confirmation of the Big Bang. The temptation lies in continuing this exploration backward in time to an era when the universe was even hotter, denser, and more compact.
It's really the light from the origin of the universe. If you have an old FM receiver, if you tune between channels, turn the knob, and it doesn't capture it and pop to a station, you get to a part where there's none, you hear a, that's what we call noise. If you have a good radio set, 1/2 of 1% of that is actually the sound of the Big Bang.
If we go tracing back in time, we encounter a period when it was too hot for atomic nuclei to form, causing radiation so intense that it could break apart any bound protons and neutrons. During this energetic phase, matter and antimatter pairs could spontaneously emerge. Further back, protons and neutrons disintegrate into a quark-gluon plasma, where the universe reaches densities surpassing those inside an atomic nucleus. Ultimately, the density and temperature reach infinite values, representing a singularity where all matter and energy converge into a single point, a point signifying the breakdown of the laws of physics. This singularity not only marks the point where the laws of physics falter, but is also perceived as the origin of space and time, in essence, encapsulated in the fundamental concept of the Big Bang. Every aspect of this journey, except for the final singularity, has been substantiated. Quark-gluon plasma has been synthesized in laboratories, matter-antimatter pairs have been created, and calculations aligning with the Big Bang's predictions have been confirmed through measurements of early universe elements and their abundances. Moving forward, observations have extended to measuring fluctuations in the cosmic microwave background, providing insights into the formation and growth of gravitationally bound structures like stars and galaxies. While the Big Bang theory demonstrates remarkable agreement between theory and observation, the universe as we perceive it presents certain features and enigmas that the Big Bang alone doesn't entirely elucidate. If everything originated from a singular point within a finite time frame, one would anticipate varied temperatures in different regions of space, as these regions wouldn't have had the chance to interact and exchange particles, radiation, or information. Moreover, remnants from the earliest, hottest periods, such as magnetic monopoles and topological defects and some degree of spatial curvature, should exist, since a singularity-originated Big Bang lacks a mechanism to balance the initial expansion rate with total matter and energy density. Contrary to these expectations, the universe maintains a uniform temperature across all regions, lacks high-energy relics, and exhibits perfect spatial flatness in every direction. This leads to two possibilities. Either the universe inexplicably possessed these properties from its inception, or there exists a scientific explanation, a mechanism that orchestrated the universe's emergence with these specific properties. On December 7, 1979, physicist Alan Guth had a groundbreaking realization, suggesting an early period of exponential expansion preceding the Big Bang. The phenomenon we now recognize as cosmic inflation could account for the universe being endowed with these specific properties from the outset. The end of inflation would then mark the transition, giving rise to the subsequent hot Big Bang. In the realm of science, one cannot simply introduce an additional idea into an existing theory and claim superiority over the new one. The burden of proof for a new theory is notably stringent. Persistent doubts surrounding established theories have recently heightened, fueled by groundbreaking revelations from the James Webb Space Telescope exploring the early universe. In its inaugural year of scientific operations, the $10 billion infrared telescope has provided breathtaking glimpses of the nascent universe, unveiling surprisingly bright galaxies from a time when the cosmos was in its infancy. With its 6.5-meter mirror, the JWST was specifically crafted to investigate this early era, a domain mostly beyond the reach of its predecessor, the 2.4-meter Hubble Space Telescope. The JWST's observations have left researchers astounded, grappling with the implications of their findings. According to the Standard Model of Cosmology, following the fiery Big Bang around 13.8 billion years ago, the universe underwent cooling, and energy transformed into matter. Over the first few 100 million years, this matter coalesced, giving rise to the first generation of stars and galaxies. While astronomers believe they had a solid grasp of this process, the JWST's preliminary outcomes suggest that stars and galaxies might have formed at a much more accelerated pace than previously envisioned. Headlines have even proclaimed that the telescope has, in essence, broken the universe and overturned models of cosmic history. Following subsequent data analysis from the JWST, some of the initial striking findings have been dismissed, and new simulations can now accommodate a few of the peculiar observations. However, certain bright, massive, and early galaxies persist in challenging theorists, implying that our comprehension may undergo shifts in the years to come. Priyamvada Natarajan, a theoretical astrophysicist at Yale University, emphasizes that current data hasn't broken the universe, but intriguing potential tensions are emerging on different scales. Resolving these tensions will necessitate researchers to reassess their foundational assumptions about galactic evolution, potentially introducing new ideas while relegating others to the cosmic dustbin. It's noteworthy that the discovery of these early galaxies is not a recent occurrence. In May 2009, astronauts installed one of Hubble's crucial instruments, the Wide Field Camera, also called WFC-3, vastly enhancing the telescope's infrared vision. As the universe expands, light traveling through space gets stretched into longer wavelengths, or the redder portions of the electromagnetic spectrum. The oldest entities, therefore, become visible in the infrared, beyond the reach of shorter ultraviolet or visible wavelengths. WFC-3 empowered Hubble to capture light from remarkable objects, including the galaxy GNZ11, which existed when our universe was a mere 3% of its current age, or approximately 400 million years old. However, Hubble faced limitations in exploring this early epoch, with few visible big bright galaxies due to the constraints in its instruments, hindering astronomers from witnessing the very beginnings of galaxy formation. Upon JWST's launch in December 2021, scientists rapidly dismissed the initial possibility of no galaxies existing within the first 500 million years after the Big Bang. The discovery of the galaxy Glass Z12, approximately 50 million years older than GNZ11, and subsequent JWST observations revealing numerous galaxies potentially as early as 180 million years after the Big Bang refuted the earlier notion. Jehan Bae, an astrophysicist at the Rochester Institute of Technology, notes the surprise among researchers at the abundance of bright galaxies detected with the JWST and their unexpected ease of identification. Additionally, these galaxies may be more massive than previously theorized. In the initial period after the Big Bang, intense conditions prevented the settling and condensation of matter into entities like stars and galaxies. As the universe expanded and cooled, conventional cosmological theories proposed that dark matter particles, outweighing normal matter about 6 to 1, gathered under gravity's influence to form massive halos. Regular matter then gravitationally clustered within these halos, eventually giving rise to the stars and galaxies observed today. Common models suggest that a galaxy comparable in size to our Milky Way wouldn't form until approximately 1 to 2 billion years after the Big Bang. However, the first JWST image of the SMACS 0723 cluster challenged these expectations. Astrophysicist Erica June Nelson of the University of Colorado Boulder identified sizable red disks, indicative of extremely massive galaxies undergoing rapid star formation. These 6 dusty, elongated galaxies appear to have existed within the initial 500 to 700 million years of cosmic history. Based on the observed brightness, Nelson's team approximated that each of these objects could weigh at least 100 billion times the mass of the Sun, with one colossal galaxy potentially housing 100 billion suns, comparable to our own galaxy. This massive galaxy might have 2 nearby companions, indicating its involvement in a galactic group, challenging existing cosmological models, according to Michael Boylan Colchin, a theoretical astrophysicist at the University of Texas at Austin. However, skepticism exists, with some astronomers suggesting that the properties of these galaxies might indicate that they're primarily filled with young, low-mass stars, making them around 100,000 times less massive than initially calculated. Nelson and her team thoroughly explored this possibility, but eventually dismissed it, deeming it reliant on too many improbable premises. An additional paper from the Cosmic Evolution Early Release Science Program, a major JWST survey team, proposed an alternative interpretation for the largest galaxy, suggesting it's situated much closer to us, over 1 billion years after the Big Bang. By applying certain assumptions to the data, they suggest that some of its light may originate from a supermassive black hole at its center, resulting in few stars and approximately 10 times lower overall mass, a perspective that Nelson acknowledges is likely correct. The challenges in early JWST science are underscored by discrepancies that have surfaced. Much of the telescope's preliminary findings rely on imaging data, where a galaxy's distance and mass are deduced from its brightness and color, an approach valuable yet bound by specific assumptions. For a comprehensive understanding of an object's properties, along with its chronological and spatial context in cosmic history, astronomers often resort to spectroscopy, a meticulous process that dissects light into its constituent colors, revealing distinctive chemical signatures. The cosmic expansion progressively shifts these signatures towards longer wavelengths, furnishing an accurate gauge of the distance traveled by light. An illustrative case involves JWST's imaging data placing a galaxy known as Sears 93316 at 240 million years after the Big Bang, initially making it as one of the most distant objects ever documented. However, subsequent spectroscopic measurements contradicted this, revealing a much closer proximity and a less groundbreaking epoch, 1.2 billion years after the Big Bang. Despite such challenges, some instances showcase the harmony between imaging data and spectroscopy. In the JWST Advanced Deep Extragalactic Survey, or JADES, 4 distant galaxies initially identified were verified to be at their extreme distances through spectroscopy. Notably, JADES GS Z13-0, the current distance record holder, thrived roughly 320 million years after the Big Bang. As the telescope's upcoming observation cycle commences in July, its spectrograph is poised to yield data on numerous objects, including potentially massive and distant galaxies studied by Nelson and her colleagues. Already, the prominent galaxies discovered by JWST are prompting theorists to reassess foundational concepts. Existing cosmological models predict the expected number of dark matter halos of different sizes across various epochs in the universe's history. Alice Shapley, an astronomer at the University of California, Los Angeles, notes a discrepancy, stating, "If we say galaxies only live inside these lumps of dark matter, there aren't quite enough dark matter lumps to host the galaxies that have been reported. Consequently, computer simulations producing insufficient dark matter halos and galaxies are losing credibility. Additional data may compel further adjustments." Astronomers at the University of Missouri and Columbia acknowledge that while there's still some flexibility regarding the exact number, masses, and formation times of galaxies, this flexibility is diminishing. Many in the field concede that their understanding of galaxy formation might need to adapt to accommodate JWST's observations. The extent of this adjustment remains uncertain, whether it'll be a minor refinement or a more radical alteration. One plausible scenario is that the earliest stars and galaxies came together more efficiently than currently believed. It's conceivable that the primordial universe was denser and more compact, potentially enabling the rapid collapse of gas and dust into stars. Boylan Colchin suggests, maybe in the very earliest systems, it's all kind of going gangbusters and there's nothing to stop it. One possible adaptation involves envisioning a scenario where a substantial number of galaxies form much earlier in cosmic history than existing theories propose. This adjustment would imply a higher efficiency of galaxy formation than current models assume. Alternatively, a more unconventional explanation involves re-evaluating the nature of dark energy, usually attributed to the observed accelerated expansion of the universe. While physicists traditionally view dark energy density as a constant since the Big Bang, conflicting measurements of cosmic expansion could prompt a reconsideration of this assumption. Examinations of the nearby universe indicate a faster expansion rate than extrapolated from observations of the early universe. Models predating JWST, known as early dark energy, propose a higher quantity of dark energy around 50,000 years after the Big Bang. These models, addressing the expansion rate discrepancy, also predict accelerated and more abundant galaxy growth in the early universe, aligning with JWST's observations. However, a significant challenge arises. The standard cosmological model, featuring constant dark energy density, has proven highly successful in explaining the large-scale structure's evolution, comprising galaxies, galactic clusters, and clusters of clusters. Any modifications must preserve these successful aspects while accommodating the new observations. While many researchers are adopting a cautious stance, refraining from discarding established ideas in favor of new cosmic perspectives, the advent of this new observational tool has invigorated astronomers, prompting them to scrutinize foundational assumptions. According to Shapley, there are moments in one's career when you realize it's a watershed moment, and the field is currently experiencing one of those pivotal instances. Now a question arises: if the Big Bang Theory is merely a theory, are there alternative hypothetical explanations for the universe's origin? The answer is yes, and here are 4 intriguing alternatives to the Big Bang Theory. Quasi-steady state theory. Steady-state theory directly contradicts the Big Bang Theory, proposing that the universe has always existed with a uniform density, devoid of a beginning. To address limitations, it evolved into quasi-steady state theory, suggesting that as the universe expands, packets of matter are continually generated to sustain density. However, this theory failed to convince scientists effectively, as cosmic microwave background data indicated a significant explosion around 14 billion years ago, marking the universe's commencement. Mirror universe theory. The mirror universe theory presents a highly speculative yet fascinating alternative to the Big Bang Theory. It posits that during the Big Bang, 2 universes originated, one progressing forward in time and the other moving backward in time. This implies that while our universe unfolds from birth to death, the mirror universe experiences a reverse progression from death to birth. An analogy to comprehend this concept is found in the movie Tenet, where objects' entropy is reversed, causing them to move backward in time. Digital simulation. In the 21st century, technological advancements have empowered humans to create and manipulate simulations of various physical aspects through sophisticated computers. As technology progresses, there's a possibility of expanding this domain, allowing humans to simulate entire universes with controlled initial and final conditions. This concept raises questions about our reality. What if our universe is simulated by a highly intelligent civilization, all determining our fates? This idea aligns with the theory of predeterminism, supported by quantum entanglement, where information travels faster than light, challenging the rules of relativity. The possibility of our universe being predetermined from its inception is intriguing. Multiverse theory. The multiverse theory suggests the existence of an infinite number of universes generated by fluctuations in dark energy, leading to multiple explosive events akin to Big Bangs. Many universes formed through these explosions may collapse to create black holes, but others, like ours, experience an explosion powerful enough to expand indefinitely. This expansion continues until all matter is sufficiently separated, creating a space of dark energy where the cycle of Big Bangs repeats, generating new universes continuously. In addition to these alternative theories, there are other intriguing hypotheses such as inflation theory, infinite universe theory, gravity rainbow, etc. While these theories have logical foundations, none has surpassed the widely accepted Big Bang theory, which, despite being the most recognized, hasn't been completely proven or fully understood. The origin of the universe remains a mystery, leaving mankind with unanswered questions.